Hey gang, welcome back to another video on thermodynamics. In today's video, we're going to talk about the general balance equation, a mass balance equation, an energy balance equation, and we're going to talk about what the first law of thermodynamics is. So let's get into it. When you have an open system, you've got mass that's flowing in and mass that's flowing out. And as an engineer, we want to account for all the mass that's entering and exiting our system to avoid an overaccumulation of material, which might lead to an explosion. And we also will want to avoid, let's say, losing a lot of mass in our system because that can also be damaging to equipment. So for us, what we want to do is a material balance around our system. And in order to do that, we start off with a general balance equation. And that's in minus out plus generation minus consumption equals accumulation. And when we think about this from the mass perspective, what we know is that mass cannot be created nor destroyed. So that means we can eliminate those generation and consumption terms. And now we can simplify our general balance equation to accumulation equals in minus out. Now you may be wondering, why do I even have generation and consumption terms if my mass balance is always going to be in minus out? And the reason why is because there are different ways you can go about that general balance equation. One is thinking about it from a mass perspective. Another way to think about it is on a moles perspective. And if you think about things on a moles perspective, then we are going to have a generation and consumption term because we are going to be making different kinds of moles and consuming different moles. And though that's really important when you're dealing with reactions, because moles make so much more sense compared to mass. But that's not something that we're going to get into in this video. That's something that you've probably seen if you've taken material and energy balances, and you can flip through some of my videos that have talked about that at a different time. So now, looking at this on a mass basis, doing a mass balance, let's convert that accumulation equals in minus out into math. So in this case, we're going to have the change in mass with respect to time is going to equal our sum of all the streams that are entering our system minus the sum of all the streams that are exiting our system. And that's our mass balance. Now, changing gears, we can think about what does an energy balance then look like? And for this, let's look back at our open system. We've got mass that's entering and exiting, and then we're going to have a whole bunch of energy terms like work and heat that are entering and exiting our system. So we're going to start off just like we did with mass with our general balance equation. So we've got in minus out plus generation minus consumption equals accumulation. And with energy, we know that we cannot create nor destroy energy. Energy can only be transformed from one form to another, which, you guessed it, is the first law of thermodynamics. Another way that a professor told me to think about the first law of thermodynamics is you can't get something from nothing. Energy can't be created nor destroyed. So if you're having trouble remembering that first law of thermodynamics, you can't get something from nothing. So that leads us to, in this situation, in minus out equals accumulation, just like when we were doing a mass balance. And now, if we want to write that energy balance mathematically, we're going to say accumulation equals in minus out. And from here, we're going to think about this on a per time basis. And we're going to look at the changes with respect to internal, kinetic, and potential energy. And similar to an earlier video, we can think about and write out those different energy terms, right? So the mass times specific internal energy plus V squared over 2 plus GH, which gives us our different forms of energy. Now, the other part, when we look at our open system, we have mass flowing in, we've got work and heat that's flowing in and flowing out. Something that we want to think about when we do the in minus out portion of our energy balance is that your masses that are entering and exiting are going to be bringing and removing a certain amount of energy into the system. And then you also have these energy in transit, which is your heat and your work. And so all of those things need to get factored in when you do the in minus out portion of your energy balance. So when we look at this, we have in minus out, and we look at if you have a mass that's flowing in, that mass is then going to also have an internal energy associated with it. It also is going to have flow work. There's work being done on the mass that's coming in. You also have your kinetic and potential energy within the system. And now we also have to consider, in the event that we have more than one stream entering our system, we need to sum all of those up. And similarly, we are going to have to think about all those streams that are exiting our system. So we're going to duplicate that exact same summation term for our outlet streams. And we also need to remember that we have heat plus our shaft work plus work due to expansion and compression. Now, looking at this energy balance, you may see some similarities with something we spoke about earlier. You may notice we have internal energy plus PV. And you guessed it, we can probably change that and simplify that down a little bit further because it's enthalpy. So we can rewrite our energy balance now with an enthalpy term rather than internal energy and flow work. So we have our in minus out. It's going to equal all those inlet terms. We can subtract out our outlet terms. And again, we'll add our heat plus work. Now, with that energy balance, the generalized time-dependent energy balance is going to be our accumulation terms equaling our inlet minus outlet plus all our energy in transit terms. And as a reminder, with the heat and the work that's entering our system, just be mindful that the sign isn't always necessarily going to be a positive. It really depends on if things are flowing into or out of your system. And we talked about that if energy is flowing in, that's where you have a positive sign. If energy is leaving our system, we would have a negative sign. Now, the other thing we can do with our energy balance is we could further simplify this if it was at steady state. And a lot of the times, especially in thermodynamics, in the early stages when you're solving these kinds of problems, you're going to be at steady state. We're going to think about things are flowing in, things are flowing out. We're not dealing with all this mass in transit. And if you get to operate at steady state, that's really nice because your accumulation term goes to zero. But there's a little bit more we could do if we want to just simplify this energy balance a little bit further for when we're doing our calculations. So we could, if we want to, and I'll flip back for a second, if we want to, on the right-hand side, we have an inlet energy term, we have an outlet energy term, or rather the summations for your enthalpy, kinetic, and potential energy. We can move both of those to the left side. And if we rearrange, this is what we get. And what you might notice is that we have final minus initial. And a lot of times what we've been doing is that's a delta term, right? That's the change of, for example, we've got enthalpy. So we have final enthalpy minus initial enthalpy. That means I can write delta H, the change in enthalpy. We can do this again for our kinetic energy because it's final minus initial, and we can then add on delta EK. Similarly, we can do that for potential energy, giving us that delta EP term. And now we can bring along for the ride the equals Q dot plus shaft work plus work due to expansion and compression. If you want to further simplify this, you can then look at your work terms. We can combine those. And now we have delta H plus delta EK plus delta EP equals Q dot plus W dot. And I wanted to show you this because I don't know about you, but for me, I know that when I see a lot of summation terms, I get a little frazzled with all these different things I have to account for. And for me to start a problem, it's a lot easier when I just have this simple equation, delta H plus delta EK plus delta EP equals Q dot plus W dot. Now, I do want to give the disclaimer that you do need to remember when you have this simplified version, you do need to account for all the streams that are entering and exiting your system. So if you have 2 or 3 different streams that are entering and exiting, you need to calculate those changes in enthalpy for all the streams. Same deal with kinetic and potential energy. Now, I'm not going to do this on the slide, but I also just want to give you a heads up that a lot of times when you're doing an energy balance, the nice thing is you can probably make an assumption and simplify this energy balance further by assuming that kinetic and potential energy are negligible. The reason why you can often assume those are negligible is that in the grand scheme of things, when you're looking at the enthalpy contributions, the enthalpy, work, and heat contributions, those are far greater than the changes in kinetic and potential energy, which is why you often could ignore and assume those are zero. I'm not going to eliminate those because I do want you to be mindful of them and wait until you see a problem statement in which it says either assume kinetic and potential energy are negligible, or the prompt gives you just enough information to make a decision yourself saying, yeah, nothing's changing for kinetic and potential energy. I can assume it's zero. So that's everything I wanted to talk about for today's video. And I want to recap that by highlighting that we talked about the general balance equation, in minus out plus generation minus consumption equals accumulation. We talked about the first law of thermodynamics. You can't get something from nothing. We also talked about the energy balance, especially at steady state, which looks just like this. And if you want to simplify it down, we can make it delta H plus delta EK plus delta EP equals Q plus W. And we also talked about a mass material balance, which was the following equation, like that change in mass over time equals the sum of all the masses coming in minus the sum of all the masses coming out. And if you wanted to, you can simplify that a little further if it was at steady state by getting rid of that dmdt term and saying it's zero. So thanks a lot for tuning in, and I'll see you in the next video.